In my previous lecture, we have discussed about how to model a systems using frequency domains, basically using Laplace transforms, where we transforms a system from differential equations, and then we transform them into transfer functions in S domains. And in this lecture, I will be focusing on how to model a control system using a state space representation, which is another method of representations. So this the state space is considered modern method, modern or time domains representations. It is a unified method for modeling, analyzing, and designing a wide range of systems. Okay. The advantage of state space representation is it can handle multiple input and multiple outputs, or we call it MIMO. And then we can, in fact, employ the systems into a real-time hardware. Okay, in a state space representation, we are only deal with two equations. The first one is the state equation. Okay, this is the state equation. And the second one is the output equation. Only these two equations. Okay, what are the equation consists of? For state equation, we have first derivative, a derivative of the state vector, which is x dot. And then we have a system metric A, state vector x. We have a input matrix, and then we have an input vector. For the output equation, we have y, which is output vector, c is the output matrix, x state vector, d feedforward matrix, u is the input vector. Okay, why only two equations? Because we only deal with current state with respect to the input and the output state. Okay, the current states and the output state. Okay, in my previous lecture, we have discussed about how to transform, how to represent systems, physical system using differential equations. Okay, this is a common example. So we have K here, springs. We have B or D. Let's put D here, damper, mass. Okay, we can then derive this using the Newton's second law of motions. Then we'll produce the representations in terms of different differential equations. So we have d squared x of t over dt plus d dx of t over dt plus kx of t ft. Okay. Okay. In previous in Laplace domain, we could model this. We can transform them to Laplace domains, which is ms squared x s, right, plus ds xs plus k xf using linear theorems, and then fs, right? Then we can find the transfer functions that represent the outputs over the inputs, which is the output is x s here, so that means x over s over f over s, which is equal to 1 over m s squared plus ds plus k. So this is in frequency domain, right? Okay, now we need to model this system from the same differential equations. This is frequency domain. Now from here we need to model into state space, right? State space, or I'll call it SS, easy. Okay, in state space, we have to, the first thing we have to do, okay, let me write again this. Okay. m t squared x of t plus d dx of t over dt plus k x t equal to f of t. All right. Then okay, we need the first step we have to do is we have to rearrange the equations. Okay, if it is we need to see what is the highest order. Okay, the highest derivative order, in this case second derivative, right? So we need to bring this as a subject of the equation. So that it's m t squared x of t over dt squared equals to minus d dx of t over dt minus kxt plus f of t. Right? So we need to keep this on the left so that we can dt squared x of t minus d, and okay, we need to just keep the derivative parts. Bring this constant down. Dx of t over dt minus k over m x of t plus same thing 1 over m f of t. Okay, we have this, and then because state space equations only has the maximum derivative is only first derivative of state vector, right? Then we have to reduce that. We have to, because we have this is the second derivative, right? Second derivative. So we need to reduce that. Okay. Now because this is x of t, right? This is the outputs of the systems. Because if you see from the model here, right? This is the outputs, this is the input, all right? Okay, now let's see this. Okay, let x of t equal to x1, right? Then we'll have this is x1, then we can say that this is x1 dot double dot equals to minus t over m x1 dot minus k over m x1 plus 1 over m f of t, right? So you see still there is second derivative, we need to use that because we know it's x1 dot, right? So we can we have to reduce the second derivative to be the first derivative. How to do that? We need to produce the first equation, first state equation, because this is a second order systems. The second derivative, that means you're gonna have a two-state equation. Okay. So this is we can assign x2 equal to x1 dot equal to x2, right? This one, right? Okay, we have that. Then rewrite again, because we know that x1 dot is x2, That is our first equation. Then x2 dot equal to minus, we rewrite again this in terms of x2. So minus d over m's x1 dot equal to x2, right? So this is x2 k over m. x1 remains at 1 s1 plus 1 over m f of t. Okay. So now we have reduced the equations from the second derivative to first derivative. So we have second equation, state equation. Okay. So ft is the input, so we can replace the ft with ut, because in our state space equations, the input vector is u, so we just replace ft because ft is our input to the systems. Then we can replace that x2 minus d over m x of f2 minus k over m x1 plus 1 over m ut, right? That's second equation. Okay, then we have completed, we have produced two state equation, because it's second order system, we need two state equation, right? Okay, now we can based on this, we can actually model the system in the state space in the matrix form like this, right? Because our state space is x dot equal to ax plus bu. This is a state equation. State equation, right? So we have this form. So x, we have x1, which is the first equation is x1, second equation is x2. So you can write this x1 dot x2 dots, right? This is x1 dot x2 dots. That is equal to the first matrix, because x1 equal to x2. This is x1 dot equal to x2. So we can write this is x1, this is x2 state vector. So since x1 is equal to x2, we have 0 here, 1 here, right? It's x1, it's x2. So x1, x2 plus B matrix. This is A, this is B. Because x1 is just purely equal to x2, then there's no component of input, we put 0 here. This is u of t, okay, right, u of t. For x2, we can get from here, x2, the second state equation, x2 equal to minus dm x1, minus km x1, right? So we have right here, minus k over m x1, which is this one. And then plus minus x2, minus d over m x2 plus 1 over m ut, right? So that's how we get this. So we get this. I think this is x1. So this is, I think, in fact, supposed to be k. This is supposed to be t. All right. Okay. And this is our state equation. Okay. This is your state equation. Then we need to find the output equation, okay, which is y equal to cx plus du, okay, cx plus du. So we know that from our models, x1 is our output, the x1 is output. So our output y equals to x1. So we need to write in matrix form. So y equal to x1, x2. So which is x1, 0, 1, 0, plus 0 ut, because there's no feed forward matrix there for this model. So we write it 0. In fact, y equal to x1, we can write in this form. Okay. Okay, now in state space representations, these two equations will represent these differential equations. Okay. Yeah. All right, let's see this. I think we just did this one from the differential equations. Then we come out with this one. Then the same thing for mass spring damper. We have this. You can convert that to this. As for the RLC, the same thing. So you just convert that to VC, because this state space is supposed to be okay, x1, x2. We can change. We can also rename x1 to VC1 or VC2. So it's just a name, but we know that this state represents the state here, VC. All right. In this case, x1 is VCT, so that means y equal to x1. Y equal to VCT is the outputs of this system. The input of the system is Vs, which is a VC in this case. So I think this probably this is supposed to be Vs. And then this is we can put ut. So same thing. All right. I think the same thing for the electromechanical DC motor. You can simply transform them to state space model. Okay, I think I will provide you some example and some examples so that you can try to solve to model and to transform between the model. All right, with that, thank you for your attention.